Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for my data management students who are reviewing for next week's Chapter 5 test. The questions we're going to look at can be found in your textbook starting on page 324. And just a reminder that the topics you need to prepare for the test are probability distributions, expected value, binomial distributions, and normal approximation of binomial distributions. Okay, so let's start looking at the questions. The first question says, a game is played by tossing 2 coins. Each toss costs $2. The player wins when both coins turn up the same and loses when they differ. The payouts are given in the table in the margin. So here's the table. The first question says, create a probability distribution for this game. Now, before I go ahead and do the math, I want to spend some time and review probability distributions. They really do form the core piece of understanding for this particular chapter, so it's important that you really clearly understand what's meant by a probability distribution. And most of the time, that means you understand the concept of a probability distribution, but you don't understand the concept of this, a random variable, or in this case, a discrete random variable. A discrete random variable is a variable, and usually we use x, that assumes a unique value for each outcome of an experiment. So in other words, when you do an experiment, whatever happens when you do the experiment has to be assigned a numeric value. So if I am tossing coins, then the number of heads might be my numeric value. If I am drawing marbles out of a bag, I might assign the number 1 if it's a red marble and 0 if it's anything else. So a valid probability distribution is dealing with numbers only. So your job is to translate the events and outcomes of an experiment into something numeric. Then a probability distribution is simply a table or graph that gives the probability for each of those numeric values. Okay, so I'm still seeing that some students are building probability distributions, or what they think are probability distributions, but you haven't bothered to assign values to anything. So for example, if I were to go up here and write a quarter, a half, and a quarter instead of this, that's not a probability distribution. Yes, there's probability in it, but this is not a probability distribution because these are not numbers. There are no numeric values. There's no x that has been assigned values. So it's a probability table maybe, but it's not a probability distribution. So again, what you need to do is this. In an experiment, each outcome is assigned a numeric value. For example, the number of heads that show up, oops, or the amount of money won. The collection of those values is called capital X, and each individual number is called xi, meaning x1 or x2 or x3 and so on. Now you can calculate the probability that each of these x's occurs, and you display the results in a table or a graph, usually a table. So now that you have hopefully a better idea, let's go ahead and actually do question 1. So part A says, create a probability distribution for this game. So because this is the first question I'm taking up like this, I want to be very formal and really review and hopefully get you to understand what a discrete random variable is. And I'm going to do that by actually assigning a variable of a definition, like you used to do back in grade 10. I'm going to let x be something. So in this case, let x be the amount of money the amount of money won. So there. So now I've assigned what x is. So now I can actually create the probability distribution. So what are all the possible values that x can take? Well, I could win $0, I could win $2, and I can win $5. And yes, it is generally accepted and proper math to organize your x so that it increases in value. So don't write 502 because the table up here says 502. You write those values in numeric order. And don't write 0 twice. 0 is one possible value for x. There's no reason why you would have two zeros as a value for x. Doesn't make any sense. Now, you also may be wondering why I'm not incorporating the $2 cost and adjusting my winnings. Well, that is a possibility, and there's absolutely nothing wrong with doing that. It's just I prefer to keep the cost of the game separate from the winnings until I need to incorporate it. So now let's go through. What is the probability that you win $0? Well, out of 4 possibilities, 2 of them are $0. So the probability there is 2 out of 4. The probability of winning $2 is 1 out of 4. And the probability of winning $5 is 1 out of 4. So there's your valid probability distribution. I don't care if you reduce your fraction, and I don't care if you turn it into decimals or not. That is a probability distribution in table format. Good. So B says, what can a player expect to win playing this game? So obviously, because X represents money won, then I'm looking for the expected value of X. And again, expected value really means the average over a long period of time. So the average over 1,000,000 plays of the number of your amount of winnings. So let's see. The formula is X times P at X plus X times P at X, and so on. So I'm going to 0 times 2 out of 4 plus 2 times 1 out of 4 plus 5. Oh, that couldn't be messier. Plus 5 times 1 out of 4. So do the math. I get 2 out of 4 plus 5 out of 4, which is, of course, 7 out of 4. But since it's a question about money, I don't want to leave it as a fraction. That's $1.75. So I can expect that if I played this game 1,000,000 times, on average, I've won $1.75. Sounds nice, doesn't it? Well, not really. Don't forget, it costs you $2. So that's why this third question is important to look at. Is it a fair game? So the definition of a fair game is that the winner and the game operator, nobody makes any money. So you expect to win exactly the same amount of money as you pay to play. So in other words, net result 0. Just, don't even play. Haha. So it does, however, say explain. So first of all, it's not a fair game. So make sure you can explain why not. So I'm going to say that I expect to win $1.75. Oh, that's kind of like a Sanskrit looking 7. So I expect to win $1.75 on average per game. But I have to pay $2 to play. Therefore, I am actually losing 25 cents on average per game. A fair game, oops, I think I put the quotations in the wrong spot. A who's a her. A fair game has an expectation of $0, won or lost. Okay. So hopefully that's clear. I know it's messy, but, it should be pretty clear. I hope. Let's look at the next question. Oops. It says 4 teachers and 5 students have volunteered to serve on the school's fundraising committee, which is chaired by the principal. The principal wishes to select the committee using a random draw. He places each person's name on a slip of paper and draws 4 names. So 4 names to go on a committee, and he starts with 4 teachers and 5 students. What is the probability that there is a teacher on the committee? So first of all, please make sure you understand that this is not a binomial experiment. There are not 2 outcomes because there could be 4 teachers, there could be 3 teachers, there could be 2 teachers, and so on. It's definitely not a binomial experiment. So it's really kind of doing old-fashioned chapter 4 math from section 4.7. So the probability that there is a teacher on the committee, well, that's a little vague. I'm not sure if they mean one teacher, like exactly one teacher, or exactly, one exactly, or do they mean at least one? I don't know. Certainly, I will make sure that when I word your test, I am not vague, because I can understand an argument in either direction as to what that actually means. Is there a teacher? Do you mean exactly one or at least one? So I'm going to show both possibilities, and it's just that way, it's a little more help for you. So in both cases, however, I need to start by looking at the sample space. And the sample space is, I am making a committee. And remember, a committee is something where order does not matter. So out of 9 people, oops, what am I doing? Out of 9 people, I need to choose 4 of them to be on my committee. So that's a sample space of 126. Now, if I want exactly one teacher, then my event space is from 4 teachers, choose 1. Then you still need 3 people, and they're, I guess, going to be students. So 4 choose 1 times 5 choose 3. And that gives me 40. So the probability of exactly one teacher is 40 over 126. And if you want that in decimal form, that would be approximately 31.7%. Now, what if I wanted the other one? At least one teacher. So my sample space is the same, but now my event space, ooh-wee, my event space is going to be exactly 1 teacher plus exactly 2 teachers plus exactly 3 teachers plus exactly 4 teachers. That's one method I could do. So I could basically do this math 1, 2, 3, 4 times and add them together. Or I could do the probability of not A and subtract. So I'm going to do it that method. Not A, the opposite of at least 1 is 0. And if I have 0 teachers, then I must have all students. So there's 5 ways of that happening. And so therefore, the probability of A is 1 minus 5 over 126. So that's 121 over 126. And again, if you like the decimal answer, you should get 96.0%. Now, I don't know if you know this, YouTube only allows you 15-minute videos, and I'm getting close to that mark. So rather than start part B right now, I'm going to have to do it in another video. So this, I guess, is video number 1, and I will meet you soon in video number 2 to continue this question and look at the others. See you there.